In this fourth year review, I'll go into several things that limit the performance of a well-designed optical system. I'll begin with the chromatic effects of glass, and then I'll move on to the geometric aberrations that blur and distort images, and then finally I'll talk about some strategy for improving the design of an optical system to eliminate those effects such as achromatization, lens splitting, and aspheric lenses. Chromatic aberration is a consequence of dispersion, which is the wavelength dependence of refractive index. Let me go over that one first. There are really two broad categories of glass. Crown glass is less dispersive, and flint glass is more dispersive. There are hundreds of distinct glass products made from a fair number of companies, with the 6 here just being the companies that popped into my head while making this slide. There are 3 standard wavelengths that go by the names C-light, D-light, and F-light, red, yellow, and blue. They're specific emission lines from hydrogen and helium. They're routinely referred to by their letter designation. Dispersion means that the refractive index is slightly different at each wavelength, as you can see in the 3rd decimal place for flint glass as well as for crown glass. As small as these variations seem to be, it's enough to have profound effects, including spreading the wavelength components of light into a fairly wide rainbow by a prism. The Abbe number is a measure of a glass material's dispersive power. If F-light and C-light are more different from each other, that is, more dispersive, then the Abbe number will be smaller. As you can see, the Abbe number of this particular flint glass is about half as large as this particular crown glass. So that sets us up to talk about chromatic aberration, which comes in 2 manifestations. There's axial color, which is the chromatic aberration in the marginal ray. So if you have a marginal ray coming in parallel to the optical axis, it strikes a lens. Light will divide into its colors. C-light and F-light are the most different of those 3 wavelengths that are used, and they will strike the optical axis at different points. So if you try to form an image only with blue light, you would find the image on the optical axis at the place where this F-light is striking it. If you try to form an image using only red light, the image will form on the optical axis where the C-light is striking it. Those are 2 different focal points. There's a chromatic focal shift, DF, the difference between where the F-light and where the C-light strikes the optical axis. When the chief ray strikes the lens, it too splits into its chromatic components. The difference between where C-light and F-light strike the image surface is the chromatic image shift. That will look like a rainbow blur on your image screen. Chromatic aberration can be seen in this photograph where the colors are smeared around the edges of this animal's ear. Lenses can be made out of multiple pieces of glass. An achromatic doublet on the left has 2 lenses, a positive crown glass and a negative flint glass lens. And by combining those and playing the refractive indices and Abbe numbers off of each other, chromatic aberration can be minimized and it can be eliminated for C and F light. So there are design constraints when you put 2 lenses together. First, the power is the sum of the 2, and then the dispersion constraint is that the refracting power of the first lens divided by its Abbe number plus the refracting power of the second lens divided by its Abbe number need to add up to 0. And when those constraints are applied, chromatic focal shift is eliminated for 2 wavelengths, C-light and F-light, because Abbe number considers their difference. But that may not be so great because you still have a chromatic focal shift between C and F-light, and it can be fairly large. It could be, for example, 200 microns. So an apochromat uses 3 lens elements and combines them, crown, and flint, positive, negative, and positive. And you get 3 design constraints from this. Again, the powers, the refracting powers divided by the Abbe numbers, and also refracting power divided by the Abbe number times the partial dispersion, P, which is a measure of the dispersion for each one of the color lines. That has to add up to 0 as well. When you do that, the chromatic focal shift is pegged at 3 wavelengths, so that now at C, D, and F light, the focal point is at the same place. And the difference is no longer on the order of 200 microns, now it'll be on the order of perhaps 5 microns. Aberrations are deviations from the spherical wavefront that's assumed by first-order optics. They're in fact wavefront errors. Wavefronts are the surfaces of constant phase in a wave, and the actual wavefront may not be perfectly spherical. It may even be rippled. The deviation of the wavefront from a perfect sphere is described by the wavefront error W. It really does describe how far off the wavefront is from where first-order optics expects it to be. Wavefront deviations are called geometric aberrations, and I'll describe 5 of them, beginning with the 3 point aberrations: Spherical, Coma, and Astigmatism. I need to refer to 2 important surfaces in an imaging system: the pupil surface and the image surface. Each surface has its own coordinate system. Theta is the angle between ρ and h. So what does that mean? Well, imagine a ray traveling from the pupil to the image. The point in the pupil is indicated with ρ, and the point in the image with h, and theta is the angle between them. You wouldn't normally expect theta to be anything other than 0, but an aberrated ray makes a bit of a wrong turn at the pupil, and it can land on the image at the wrong angular coordinate. Now, an ideal wavefront, being spherical, is described by a second-order polynomial proportional to h squared. But the real wavefront is described using an even-order polynomial in h, ρ, and cosine theta. This is the function that's going to guide my discussion here. Since the real sphere is second order, the deviations are fourth order, or sixth order, or higher. I'll focus on the fourth order terms, although higher order aberrations present as big a challenge to designing a good imaging system. Aberrations result in poor image quality because they cause rays to reach the image surface at the wrong point, resulting in a blurred image. Each term in the polynomial expansion of the wavefront has a distinct physical meaning and degrades the image quality in a unique way. Piston actually doesn't affect image quality since it doesn't lead to a blur, but the rest of these do because they start in the pupil, beginning with spherical aberration, which depends only on the radial coordinate of the ray in the pupil. Curvature of field depends quadratically on both coordinates, as does astigmatism, which also brings in a rotation of the ray as it transfers from the pupil to the image, similar for coma and distortion. Each term in this expansion was given its name due to the qualitative feel of its effect on the image. And because each term is a separate coefficient, it's possible for one or even more of them to show up strongly in a lens, while others are barely noticeable. Because the converging wavefront is spherical, it converges to a point. Failure to perfectly converge to a point is what is meant by aberration. The wavefronts are aberrated, but that translates into a description of the rays as well. T is the ray aberration, and it's the derivative of the fourth-order wavefront aberration, which is why this is referred to as third-order ray optics. Next, I'm going to examine each of the 3-point aberrations, beginning with spherical aberration. The focal length of a lens has a little bit of variation at higher heights above the optical axis, and that, in fact, is what spherical aberration is. The higher a ray is above the optical axis, the farther from the paraxial focal point it will be when it arrives at the optical axis. A paraxial ray comes in parallel, arrives at the front surface of the lens, refracts, and refracts at the back surface, and then arrives at the optical axis at the paraxial focus. A ray that comes in lower will also strike the optical axis at the same point, in which case you can say that these two rays are focused. They are paraxial rays. They're close enough that they both meet at the paraxial focus, as opposed to a ray that comes in farther up, for example, the marginal ray, which is way at the outer edge of the lens. It will arrive at a different point. The distance between the focal point for paraxial rays and the marginal ray is the longitudinal spherical aberration, and it could be either in front of or behind the paraxial focus. If the longitudinal spherical aberration is behind the paraxial focus, it's referred to as negative spherical aberration. And that's typically the case for a diverging lens. A converging lens will usually have positive spherical aberration, though not always. Let's follow some rays as they come in, beginning with the marginal rays. Where they meet is the marginal focus. The paraxial rays come in and meet at the paraxial focus. And really all rays that are close to the optical axis will meet at the paraxial focus. The separation is the longitudinal aberration. The rays that are between the paraxial bunch of rays and the marginal rays will have a meeting point that's somewhere between the marginal and paraxial focus. Put a dot every place a ray meets its neighbor. What you get is something called the caustic. Although all of these rays don't focus to a point, there is a point along the optical axis where you might expect to get the best image, and to find that point you need to find the circle of least confusion. You find it by looking at the marginal ray from one side and look at where it crosses the caustic on the other side, and that will be the point where the focus is the best. You have the minimum blur, or rather the circle of least confusion. And that's the best place to put the screen to view the image. If you're imaging a star, you'd expect to see a point on the screen, but instead you get this blurred out image, which has a circular pattern that's independent of the azimuthal angle. It's the same as you go all the way around the circle. That's a fingerprint of spherical aberration. There's no angle dependence on the screen. Between the minimum blur and the paraxial focus, there's this nice blurry image. And at the marginal focus, it's a crisper pattern, but it's still less focused than it is at the point of minimum blur. Spherical aberration shows up as the circular symmetry in these patterns, not the radial variation. So these rings that you're seeing are something else. That's diffraction. People were alarmed about the image quality from the Hubble Space Telescope when it was first commissioned. The image blurs were orders of magnitude worse than what was anticipated. Because the telescope was designed to be diffraction limited, the blur from aberration should have been smaller than the diffraction blur from the 2.4 meter aperture, which should have been only a 0.01 arcsecond spread of rays, known as the point spread function, turned out to be a blob that subtended 4 arcseconds. The cause of this disappointment came down to spherical aberration, and the blur from that was improved pretty significantly after correction optics were installed in a later mission. Coma is the next point aberration. It's called an off-axis aberration because it's only seen with rays coming in at an angle. Marginal rays are subjected to a slightly different magnification than paraxial rays, resulting in the rays finding their focus at different heights above the optical axis, either closer to the optical axis as in positive coma, or farther from it as in negative coma. Coma affects sagittal and tangential rays differently. Tangential rays approach along a vertical axis, as opposed to sagittal rays which approach along a horizontal axis. Of course, both are present at any time as the whole pupil is peppered with ray traces. When the field angle is 0, there is no coma, and as the field angle grows, coma becomes more acute. Let's arrange for this square pattern of parallel rays to pierce the entrance pupil, in this case just this lens. All of these rays should focus to the same point, but let's map out what becomes of these rays when they arrive at the image surface. Instead of a single well-focused point, they'll form a snowman. The chief ray which penetrated the center of the pupil is now at the top of this arrangement of spots, and the marginal rays are at the very bottom of it. The term coma, which is the tail of a comet, is used for this kind of aberration. The separation between where the chief rays and marginal rays arrive at the image is the tangential coma, and the half-width of this blur is the sagittal coma. Now translate to another image plane, and the pattern grows from the paraxial focus, which in the absence of other aberrations is still the highest quality image point. The image of a deep sky object affected by coma is shown on the left. A commercial off-the-shelf correcting lens is used to remove that coma, and you can see how the unaberrated image on the right is quite different. You can also see why it's called coma. The aberrated image looks like the tail of a comet, which, by the way, is called the coma. You can't completely eliminate point aberration from a lens element, but since aberrations are connected to the geometry of surfaces, you can at least manage them. Here's a range of converging lens shapes and orientations. On the left and right ends are convex meniscus, either with the concave surface facing the image side or the object side. And then there's plano-convex and equiconvex. All lens shapes fall somewhere on the spectrum of shapes, and where they fall is described by the Coddington shape factor. The values of the transverse ray displacement of a single lens element can be computed for spherical and coma, and it turns out that 0 coma is possible if this shape factor equals 0.8. Spherical aberration can never be 0, but it can be minimized at a shape factor of 0.714. So coma and spherical are minimized when the shape factor is nearly, though not quite, plano-convex, with the convex side first. Astigmatism is a result of tangential and sagittal rays having a different focal length. Tangential rays are rays on the meridional plane. The sagittal ray fan is perpendicular to the tangential ray fan. They pierce the lens, and the sagittal rays and the tangential rays focus at different places. And that's what happens with astigmatism. Two different focal lengths depending on how they pierce. A source on the axis will not produce astigmatism, but as you get off the axis, you can see astigmatism happens because, as you can see by looking at it, the tangential and the sagittal rays strike the lens differently. Take a look at the tangentially oriented rays striking the lens and then converging at a point called the tangential focus. There's no screen at the tangential focus stopping the rays, so they continue on. By the time they reach the medial focus, whose name will become evident soon, the nice point they previously made has stretched into a vertical line. Now rotate around and look at the same lens from above. Now you see the sagittally oriented rays leaving the object and striking the lens at all different points along this line, and then converging to a point that we'll call the sagittal focus. When the sagittal rays were still at the medial focus, the nice point that will later form when they do get to the sagittal focus is stretched into a horizontal line. So at the medial focus, rays are landing with a footprint in an oval shape, with the vertical dimension defined by the tangential ray fan and the horizontal dimension defined by the sagittal ray fan. This is the point of best focus for a lens plagued with astigmatism. There are two more third-order aberrations that move the location of the focus, but rays still focus to a point, just not the point that's expected. These are Petzval field curvature, which moves the focal point off of the plane that contains the paraxial focus, and distortion, which moves the location of the paraxial focus on the image plane. Because rays originating from a field above the optical axis focus closer to the lens, Petzval causes an image blur around the edges of the image if a planar screen is being used when what's actually needed is a curved screen. Field curvature is a field-dependent defocus. It's a result of the various surface powers and refractive indices inside of an optical system, and the consequence is a curved image surface, where in both the sagittal and the tangential directions, the image lifts off of the paraxial plane. It might go in front of the paraxial plane or it might go behind the paraxial plane, but the image surface will be this spherical bowl that has its vertex at the paraxial focal point. You can imagine how this has to happen if you consider rays. They'll all strike an image surface, but if they're all going to go the same distance, the image surface that they will strike will be a sphere, and the radius of the sphere is called the Petzval radius. The contribution of each lens element to Petzval curvature depends on whether that element is converging or diverging. A negative or diverging lens element produces a convex Petzval surface, but a positive or converging lens element produces a concave Petzval surface. So by combining positive and negative elements, it's possible to cancel the Petzval curvature and realize a flat image field. This usually requires a final negative element, since imaging lenses are net positive. They have to be, or they wouldn't put an image on a screen. The field flattener, as it's called, is usually positioned right in front of the paraxial focus so that it flattens the image surface without otherwise significantly influencing the image. But it doesn't need to be there. Field flattening can also be accomplished by judicious selection of the lens elements in the compound imaging lens. Petzval moves the best focus point off the image plane, and distortion moves the best focus point to a new location on the image plane. As with the other aberrations, distortion comes in a positive and a negative form. Positive or pincushion distortion causes lines that are straight in the object to bend inward in the image while at the same time making the image larger. With negative or barrel distortion, straight lines in the object bulge outward while at the same time making the overall image smaller. Positive distortion occurs in zoomed-in telephoto lenses. Zoomed-out lenses can exhibit negative distortion, with the most extreme case of negative distortion probably being wide-angle lenses. Positive distortion is so called because points in the image move outward. What should be a rectangle in the bottom left image has each of its points relocated to points that are radially farther out, with the opposite being the case for negative distortion. The farther a point is from the center of the image, the larger the displacement usually. So distortion is a variation in the magnification with distance from the center. When both positive and negative distortion are found in an image, the result is mustache distortion. Straight lines are curved into something that sometimes resembles a handlebar mustache, with points in the center of the edge possibly moved outward and points near to the end of the edge possibly moved inward, giving Mona Lisa wide shoulders with small hands and a small head. Several things are happening during optimization, and one of them is this practice used in optimizing lenses called lens splitting. The idea is that the various aberrations in a lens depend on the refracting power of the lens, and specifically for thin lenses, there are well-established equations showing that the spherical aberration is proportional to the power cubed, Coma, power squared, and astigmatism and Petzval are linear in power. Power is just 1 divided by the focal length of a thin lens, but what that means is that the aberration produced by a thin lens depends on the first-order property of focal length. So the spherical aberration, Coma, and astigmatism have these various functional dependencies on power, with A, B, and C being constants that depend on something called the structural aberration coefficient. Now, instead of this single thin lens with focal length f, or rather power phi, you could divide it into two lenses of half the power. They each have power phi over 2. Half the refracting power means that this lens is half as effective at converging light. Its focal length is twice as long. But if you have two of them, you recover that focal length. You can achieve the exact same first-order optics by just splitting the lens in two. Now, what's the benefit of that on image quality? Since spherical aberration goes as power cubed, each lens element produces 1/8 the spherical aberration that the original lens element produces. So with two of them, you've reduced the spherical aberration by a factor of 4. You've reduced the Coma by a factor of 2. The astigmatism doesn't change, so you need to find other ways to minimize astigmatism, but those other ways are also available in the optimization procedures. Aspheric surfaces are a very powerful way to beat down the aberration. Surfaces on the glasses and on the mirrors don't need to be spherical. They can be elliptical, parabolic, or hyperbolic. A surface can also be described with a high-order polynomial, and that's where they become very powerful. Surface sag of a spherical surface is a really quite simple expression, but it's a very complicated expression if you have a polynomial description of that surface. And every coefficient of that polynomial, down here it's A4, A6, A8, becomes a quantity that can be manipulated in order to minimize the aberrations. If you use a high enough order polynomial, you can start to customize every spot on the surface in order to beat down the aberration that's being caused by that spot on the surface. In a typical compound lens design, some or all of the surfaces could be aspheric. It's fairly common with mirrors, especially use parabolic mirrors, and for systems that use plastic lenses, it's fairly common. such as this cell phone lens, which has 6 lens elements in it, every one of which is aspherical. And you can tell by looking at these 6 elements that those surfaces are not spherical, especially that one all the way to the right, which is referred to as a gull wing lens because of its shape. Looks like a bird. Sometimes the departure from spherical is subtle, but sometimes it's like these. So thank you for joining me in these 4 review videos of the 4 years of optics. The slides in these videos were made from lecture notes that I've been using in various courses that I have taught, and I hope came together as a useful summary of the geometrical optics half of geometrical and physical optics.